Okay, I need to say okay to this. Is everything all right? Okay, let's close the door. Hello, everyone. Welcome to the second lecture of Seminar in Computer Architecture. So today it will be more like a lecture rather than a paper presentation. And the purpose is to give you the foundation of the topics related to memory robustness. So there are a lot of slides, and I'll be just going over them quite fast. But feel free to stop me. We will spare some time to discuss. Discussion is better. I prefer discussing more than covering all the slides. So my name is Giray Yağlıkçı, and there should be a okay. This is my brief self-introduction. I'm a postdoctoral researcher in Safari in ETH Zurich, and I've been doing research on memory robustness quite a while now. And my research interests are computer architecture, hardware security, memory and storage systems, and robustness in general. So let's start with looking at this picture. How reliable, secure, safe this bridge, do you think? It looks nice, right? But due to some engineering and building mistakes that is done on the way, it miserably failed at its time. You might think that these people are fine. They're like enjoying their time, having lunch together, but we do not know what is going to happen in the next moment, right? So the security or robustness in general is about preventing unforeseen consequences. And for example, this car is with a remote control, maximizing its storage capacity inside the car. The driver is on top, and it looks like it works fine, but it might not work fine all the time, right? So we do not want these kind of risks, and we want our systems to be robust. So today we will mostly talk about RowHammer. So I will begin with explaining that. So RowHammer is a phenomenon where in your memory chips, one can predictably induce bit flips using some software. And this is a simple hardware failure mechanism that is triggered by software, and it's widespread across a lot of systems. So you might have seen RowHammer in like various popular science articles as well. And as I will show in a bit, there are a lot of research papers on this as well. It's a hot topic today. But let's take a step back and talk about why memory robustness is important. So this is a paper from 2013, actually foreseeing the upcoming challenges of memory due to memory scaling. So let's talk about memory technology, the prevalent memory technology, DRAM, dynamic random access memory today. DRAM stores charge in a capacitor. You see the capacitor here, and you access this capacitor through this access transistor, and through the bit line, you sense the voltage and understand if it's 1 or 0. So as the DRAM manufacturing technology scales down, you have denser chips. You can put more gigabytes into a single chip. But as a result, your cell capacitor gets smaller, and they get closer to each other. And as a result, accessing one capacitor can disturb other capacitors as well. So there are some pictures here that I'm not going to go through, actually, that shows how these cells are laid out in DRAM chips. This is a more recent picture from some DDR5 chip, where you see like these cells being super close to each other. Another earlier research paper from 2015 looks at the data failures in all of the Facebook servers worldwide, and they show that you get more server failures as your DRAM chips get denser. So on the x-axis, you see the DRAM chip density in gigabits, And on the y-axis, you see the failure rate. And there's a clear increase. So there's a full reference for that paper. And this shows us that the memory scaling is really challenging today. It reduces robustness, although it increases capacity. And we need to be careful about that. And we need to understand all sorts of failures. And that's where comes the infrastructures to understand such issues. So you want to understand this. This is such a field that if you do your job greatly, then nobody notices the problem. And to do it greatly, actually, you need to find out the problems, the robustness issues in your chips before they actually affect the systems widespread. And for that, you need to have some infrastructures to test them. And we built like several different infrastructures over time for different purposes. I hope it still works. Okay, so I'm going to focus on one of them. This one paper that uses these infrastructure. So this is the infrastructure that we use there. So this is an FPGA-based infrastructure where we test our DRAM chips, and we have a temperature controller, PC here, lots of FPGAs. Each of them, I cannot see my cursor. I guess, oops. Okay. We have lots of FPGAs connected to some DRAM chips, and we run some tests on these FPGAs, analyze the data, and see if bit flips occur in various conditions. So we later on open source this infrastructure. So if you have the FPGA board yourself, you can also do it at home. But we have like multiple, actually more than 50 instances of these infrastructures available in ETZ building. So if you're curious to try something out, you can reach out to us, and we can manage something together, and you can use our infrastructure. So this is an infrastructure that's flexible, easy to use, and it's open source. And this is the full reference, and this is a reference to the updated version of this. We have many of these as well that we can test DDR4 DRAM modules in a really fine-grained way. So it supports like a lot of different, well, 5 here. I guess it's more now, different infrastructures. So you can just download this from GitHub to your FPGA, and then you can run it. Okay, so let's talk about data retention memory. So as I said earlier, DRAM cells are, they store a bit of data as the form of charge in a capacitor. And it means that that's a leaky kind of circuit, actually. There are a lot of leakage paths, and it loses charge over time, meaning that it's a volatile memory technology. And therefore, we need to care about the data retention time. So when we test real DRAM chips, this is data from 2012. I believe it's from DDR3 DRAM chips. There's a small fraction of DRAM cells that retain data between 64 and 128 milliseconds. And another small fraction holds up to 256 milliseconds, and then the vast majority of that can hold data or retain data more than 256 milliseconds. So you do not see this kind of breakout if you do not test the chip yourself. And if you look at the specifications, they tell you that you need to refresh all these cells, meaning like read the data and write it back once every 64 milliseconds. So you actually do everything for the worst case scenario. Okay, so there's a paper here that leverages that heterogeneity in DRAM cell behavior and improves performance. And it's also worth noting that last year in ISCA conference, they collected the they collected the most impactful papers in the last 25 years and invited some retrospective issue, and this is one of them. Another one of them is this one, an experimental study of data retention behavior again. It was also published in ISCA 2013. a similar story. So similarly, so DRAM is not the only memory technology. We also have NAND flash chips, which is not volatile, and but they have their own robustness issues. So we also have some infrastructures we built over time to test those chips as well. So basically, you need to go across the all sorts of memory technologies actually to understand all these memory robustness issues. Okay, and I will just skip this paper. Okay, let's go back to a curious phenomenon, which is called RowHammer. So I will explain RowHammer in a little bit more detail now. So modern DRAM is prone to read disturbance errors, meaning that when you access a cell, it creates a noise on other cells physically nearby it, and it can lead them to lose their charge a little bit more. And when you do this many times, then you can cause them to experience some bit flips. So here in a DRAM chip, we organize DRAM cells in a two-dimensional array, and internally, so there are rows and columns, and internally we access them in a DRAM row granularity. So when you access a DRAM cell, you access the cells in the whole row. And let's say you want to access data in this middle row, you must open it by putting high voltage, and then you can access. And once you're done with that and you want to access another row, you need to close it by applying low voltage. So if you do this operation many times, this voltage swing over there affects the rows physically nearby it, and you might see some bit flips around it. And this is something that we do every day, basically. Like this is some phenomenon that works really reliably in that sense. So we call the row that is in the middle the hammered row that we keep opening and closing, and the victim rows are the rows that are affected. Okay, so these are some results from a paper published in 2014, about a decade ago, and we show that these are all DDR3 DRAM chips, and the companies ABC are, I don't know in which order, but it's Samsung, Micron, and Hynix. These are the major manufacturers of DRAM chips today worldwide. And if you look at the market share, the cumulative market share of these companies, it's like more than 96% or something like that. So today, if you go to Galaxus and Digitech and buy some DRAM module, probably you will end up with a chip manufactured by these guys. And we show that more than 80% of the DRAM chips are vulnerable to this phenomenon. So it's really widespread. And if you look at the, okay, so here's an analysis of when these problems actually occurred in real DRAM chips. So if you look at this laser also doesn't work. Okay, maybe I should just point like this. So if you go for really old chips, from 2008 to 2010, for example, you do not observe any bit flips. They are safe, but they have really low density and they are really slow. So you're actually bargaining if you want faster chips with higher capacity, or you want more robust chips in this sense, right? So ideally, we want both. We want high capacity, fast, and robust. And in 2010, we have the first appearance of the bit flips. And as you go for the newer chips, the bit flips start occurring everywhere. And this is happening because the DRAM cells are too close to each other, and access to one cell affects the electrical charge in the other cells. And when we activate a row with high voltage, it causes the other row to lose charge a little bit more. So this is something really low level, what I explained. It's really, so this is the whole stack of computer, and this is a phenomenon that really happens at the electrons and devices level, at the very bottom, right? And as a user, you need to care about all these, actually. But as a programmer, for example, you want to focus on your problems and algorithms more, for example, right? And the vulnerability here can be exploited across the stack and attack your software actually. So let's see how it's done. So this is a very simple code that you can run on your computer. It's also available on GitHub. You can just download and compile and see if you will see any errors on your computer today. Probably if your computer is new enough, the active countermeasures will mitigate most of the bit flips, so you might not observe today. But if you're like persistent enough, if you're really stubborn about it, you can make it work. So basically what you do is you have these two rows that you want to access. The first move accesses this, and then the next move accesses this. And then when you do CL flush, it basically flushes the copy of this data inside the cache to back to the memory. And then once you do this fence as well, you avoid caching the data that you already fetched. And when you do it in a loop, you can observe bit flips everywhere. So they run this in 2014 or 13 in different CPUs, Intel Haswell, Ivy Bridge, SandBridge, and AMD Piledriver. And in all of them, you see errors. So this test is actually adopted very quickly in 2014 by memtest86. This is like a tool that you use to test your memory chips, basically. There are a lot of details about that. I'm not going to go over them because of time restrictions. So this is the whole. This is a screenshot from the paper, and this is the link for the paper. And I will talk about another work called from Project Zero. It's a part of Google that exploits this vulnerability in a system level to hack computers. So let's see how they do that. So this is what they say. One can exploit RowHammer to take over a system and read the data they do not have access to, and break out virtual machine softboxes, corrupt important data, and steal secret data. So let's see how they do that. I'm not going to go over this. Let's explain from here. So how many people are aware of virtual memory? Okay, quite a bit. Okay, so as you know, we have pages in memory, and we have page table entries that shows us that points to the physical pages when we want to access a virtual address, right? So this is after the translation. You have some bits spared for the physical page addresses, and you have some other bits to control your access permissions to those. So let's say you want to induce a bit flip in this page table entry, and you want to gain write access to a particular page. So you have like 1 bit for the write access in this whole 64 bits. So it gives you just a little bit of chance to have the bit flip over there. So what they do is that when you look at the physical page base address, you have many more bits over there. And if you can induce some bit flip over there, you can change which page this page table entry points to. So you basically, so this is a pointer for you, right? So you change a bit in the pointer, so it points to some different location. So from virtual address space, we want to go to this physical memory page frame, right? And to do that, we first need to go to page table entry, read the page table entry, and go there. So what they do, they allocate this memory in the virtual address space many times, such that it creates lots of page table entries pointing to this address. And they fill up the whole memory with page table entries. And what happens once you access this page table entry, it points to here, right? So everything is fine now. And then if you somehow keep accessing these rows and induce bit flips in this entry, then it points to some different address. So now you have write permission for this address. And this itself is a page table entry. So you can change the data inside it very easily because it's just a regular write access at that time. And then once you access this, it points to some other place. So by repeating this, you can actually write whatever you want in the whole memory. And by doing that, you can get like kernel privileges, basically. Yeah, there's a summary of that. So this is what Google showed just like 1 year after the discovery of this widespread phenomena. Okay. And this is a good analogy. It's like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you were after. It's just like good analogy. Okay, so this happened in 2014-15, right? And many researchers, there are a lot of smart security researchers. You might know some of them. They exist in ETH Zurich, and they do a really great job in some other places as well. So there are tons of system-level attacks that exploit this phenomenon. So they do RowHammer attacks using JavaScript code just on a web page, right? They do that in mobile systems. They use GPUs to accelerate their attacks. They use network packets to hammer rows and induce bit flips, so you can actually attack remote machines. Another example of that. You can be in you can instead of like taking over the system, you can silently steal some information by using RowHammer. So I'm not going to get into details again, but the main key idea behind this is that your RowHammer vulnerability is quite sensitive to data pattern you put there. And by observing which bits experience bit flips, you can actually get a mask of the sensitive data in the other row, and you can actually steal some information by exploiting that. You can pinpoint some bit flips in some locations, and that locations might be hosting some neural network weights, and you can reduce your 90% accurate model to 10% accurate model. So this is really a safety issue, right? Just imagine that this kind of neural net is running on a self-driving car, and somehow you find out a way to send some network packets to induce RowHammer bit flips in that car, for example, or you download an app from App Store to that car, and you reduce the accuracy, and then now your pedestrian is recognized as like nothing, or I don't know. It's really a safety issue. Okay. So these were the early works from like 2014 to 20, basically. And in 2021, people also, this is a Google work, basically, that shows different access patterns. So half double is a different access pattern that significantly reduces the, basically like overcomes. Okay, maybe I should say this first. So until 2020, 2021, DRAM manufacturers started claiming that, okay, we put some countermeasures inside our DRAM chips, and now they're not RowHammer vulnerable at all. You cannot induce bit flips. And they put some like very low cost and not super secure mechanisms inside their DRAM chips that we figured out later on. And this is another paper from Google, not from us. It's showing that you can do some tricks in your access pattern and bypass these mechanisms by reducing the necessary activation count to induce bit flip. It was also published in Usage Security. Okay, so there is a retrospective paper that actually explains all these in a really nice way. And there's an updated version of that as well, published in 2023 January, 2 years ago. Right, 2 years ago, yeah. And there's a retrospective paper from ISCA's 15 year as well. So this is 2024, I guess. Yeah, no, this is 2023. Okay. So you can check those papers to get a really clear picture that I don't have time to cover. Okay. So this is one of the recent papers that I wanted to mention. In 2024, this is published in June. So DRAM SAC is DRAM security. It's a workshop that is collocated with one of the major conferences, ISCA. And Salman Kazi is an expert in Google. Daniel Mogimi is also from Google. This paper investigates the vulnerabilities in Samsung's last defense paper, and they show how they hack it, real nice way. There's another paper. This is from ETH Zurich. This was published in one of the top security conferences, user security in 2024, from Kaveh Rezavi's group, and it's called RowHammer. It's one of the few papers that show RowHammer bit Phillips on AMD systems, AMD Zen-based particularly. And a really important thing in that is, in my opinion, is that among a lot of DRAM modules that they test and show bit Phillips, there are also some DDR5 modules that are considered like RowHammer safe. And DDR5 is really like the state of the art now. If you bought your computer like this year, probably you have DDR5. We still have some bit Phillips in those, even though it's harder to induce because there are some countermeasures, but it doesn't completely fixes the problem. And this is really a sign that, you know, we shouldn't just like patch this problem if we want to completely get rid of it. So it's really important to understand why it happens. It's really important to test real chips to see what level the vulnerability is, and we need to have really robust mechanisms to avoid these bit Phillips in all conditions. I'm running out of time, I guess. Okay, this is my thesis that has a extended related work section that you can check. And also, overall, the thesis, I'm proud of my thesis, so I wanted to put that here. Okay, so let's look at some works on understanding RowHammer. So Philippine Bits is the first work that is published in 2014 and invited to this 50-year thing in later on. I already showed the infrastructure. So we tested lots of DRAM modules manufactured from 2008 to 2014. We show that RowHammer, most modules are at RowHammer risk, and we either have errors or we need to go for older chips. And errors occur because of the charge loss. And adjacency is important. The RowHammer effect appears in the close proximity of a DRAM cell in the physical domain. And we have lots of sensitivity studies and other results in the paper, and we also explore the solution space that I will talk about in a bit. So this is just showing the locality of the RowHammer bit Phillips. So we hammer the row at address 0 here, so it's the relative address to the aggressor row. And as you see, the bit Phillips are accumulated in ±1 row addresses. And there are some bit Phillips here and there as well. Okay. Okay, so if we look at the access interval, the more frequently we access aggressor row, higher bit error rate we achieve. So this is initial finding, right, in 2014. So I will talk about another paper later on that actually shows to twist this a little bit more. So don't take it as granted. Okay, so here's the refresh interval. So let's say in our system, we keep hammering rows, and there's no mitigation mechanism, and we just periodically refresh rows to avoid bit Phillips. And what this paper shows that if you refresh all rows at every 16 milliseconds, which is like 4 times smaller than the nominal refresh period of that time, you do not observe bit flips. Well, you observe some bit flips actually. In some modules, you don't observe some bit flips. But if you look at the other refresh intervals, so as you refresh less frequently, you observe a lot of bit flips. So you basically need to increase the refresh rate a lot, which is not practical. You don't have time for that. And it's really dependent on the data pattern. So if you alternate the ones and zeros, then you get an order of magnitude more errors. And there are some other key observations, but I'm not going to go through them. This is the full reference. And this is an updated version of that, not updated version of that paper. So that paper was in 2014, and this is in 2020. After 6 years, after DRAM manufacturers claimed that they fixed the problem and there's no RowHammer issue in the current DRAM chips, we went to the field again. We collected lots of DRAM chips and we tested them. So this is a study of that. And we also collaborated with Microsoft to test Microsoft servers to develop methodologies to understand, can we easily identify the susceptible chips to RowHammer in a cloud environment? The answer is not that easily. We looked at some other dimensions. So RowHammer has many dimensions. This paper looks at temperature sensitivity, plays with access patterns, and looks at the variation across DRAM cells. This paper looks at the voltage scaling. If you scale down the voltage of the DRAM chip, you can actually reduce RowHammer vulnerability a little bit. So we quantified how much. And we also looked at HBM2 DRAM chips. This is almost state of the art. So today, like most systems have HBM3 rather than HBM2. But if you go for FPGA platforms, you only find HBM2. So that's why we tested HBM2. And we show that it's also as vulnerable as the DDR4 chips. Okay, this is published in DSN last year. And another work that looks at the spatial variation of read disturbance vulnerability or RowHammer vulnerability across DRAM chip, DRAM rows in a chip, and leverages the heterogeneity basically to reduce the costs of the RowHammer solutions. Let's look at some RowHammer solutions in the remaining time. So this 2014 paper defines two sets of solutions, one immediate, one longer term. So immediate solution means that you want to solve the problem today. And the only way that you can do that is via software patches. And you don't have many possibilities about that because you cannot change the deployed hardware. You can only update the software, right? The most you can do about the hardware is updating the firmware. And it only works if your hardware is already programmable or already supports the new features that you will introduce. The longer term is actually look at the architecture, look at the memory controller design, look at the DRAM chip design, and fix it for good. So this Cisco 14 paper actually discusses 7 solutions that are from both immediate and longer terms. And as the best solution among those 7, it proposes PARA. Before going to PARA, I'll talk about the high-level approaches of these RowHammer solutions. So the most straightforward thing that you can say is that more robust DRAM chips, right? Just make the chips better. I don't care. But it's really challenging. It really requires a lot of investment, a lot of research. It's not something that you can easily solve with money as well. And you can deploy some error correcting codes to fix the bit flips, basically. You can increase the refresh rate. This is one of the immediate solutions that is not scalable at all because you cannot, with today's vulnerability, you cannot refresh frequently enough to avoid bit flips. You can enforce some physical isolation between between the address spaces of the potential attacker and victim. But it doesn't work actually because it defeats the purpose of increasing your density. Now you put a lot of isolation rows, you do not have as much density. Reactive refresh, this is one of the most popular ones. So you somehow need to identify which rows are most rapidly activated or hot rows so that you can refresh the neighboring rows. And the last one is proactive throttling. You slow down the memory requests basically so that no one can hammer rows frequently enough to induce bit flips. So as you might imagine, there is like a huge trade-off space among these that's regarding cost, power, performance, and hardware complexity. So when we look at Apple's solution I guess it was in 2014. Yes, no, maybe 15. They basically increased the refresh rate. That was the only thing that they could have done at that time, and they did it, and it's fine. But today it doesn't work. Okay, let's look at our first solution, Para. It's probabilistic adjusted row activation. So the key idea is we do not want to identify which rows are most frequently accessed, but we know that some of them are most frequently accessed, right? So when you close a row, you just like roll a dice, throw a coin, generate a random number, and with a low probability, you refresh the rows next to the row that you already activated. And it provides a quite good reliability guarantee based on the vulnerability level of that time. And if you change this threshold, so how it works is that you generate this random number, you compare that random number against this threshold. So random number is between 0 and 1. And if it is smaller than this, basically 0.5% probability, you refresh the rows. If you change this threshold, you can refresh the rows more frequently or less frequently. And in a bit, we will see that that's exactly what Intel did. So Para refreshes rows infrequently, so it doesn't incur a lot of power and energy overheads, and it's stateless. It has low cost and low complexity, and it's effective. I'm going to skip this and show that this is a BIOS setting. Basically, here you can choose your RowHammer solution as hardware RowHammer protection or 2 times refresh. And if you choose the RowHammer protection, you can set the probability here. So this is one of the good examples of the real impact of research in real products, right? Okay, this is the full paper. And takeaway is that main memory needs intelligent controllers for security, safety, reliability, and scaling. Okay. These slides are here just to say that the similar issues exist in NAND flash memories and solid-state drives. We need to look at them as well. We are already looking at them. So I'm not going to talk about them, but if you're interested, please reach out to us. So there are 2 major RowHammer directions: understanding RowHammer and solving RowHammer. And there are many effects that are still not really well explored. So we do not know how DRAM chips age over time and how the RowHammer vulnerability changes, and how are they affected by environmental conditions. We didn't exhaustively explore memory access patterns. So we explored some of them. We are still exploring some other, and there are many more to explore, basically, to investigate. And we need to revisit every memory controller and system design decisions, basically, to understand how can we solve RowHammer or how they affect RowHammer. Solving RowHammer, on the solving RowHammer side, we need to look at flexible and efficient solutions. Solutions should be patchable after deployment, and hardware software co-design is quite important in this sense as well. So today I will show in the next hour that today you can easily, not easily, but fairly easily, you can avoid RowHammer bit flips, but it comes at the vulnerability of denial of service attacks. Now, your malicious users can trigger these RowHammer defenses, create a lot of refreshes, and then hog the memory bandwidth. and you end up like slowing down the whole system because of that. So these are the things that we need to look going forward. Okay. So I have 4 minutes until the break. I'll quickly talk about this Revisiting RowHammer paper from 2020. So in this work, we tested 1580 chips. It's like a lot of chips. And we show that newer DRAM chips are way more vulnerable to RowHammer. And if you look at the 2014 paper, you need around like 75,000, 80,000 row activations to induce a bit flip. And if you look at this paper, after 6 years, tested the same phenomenon with newer chips, and it shows that only 4,800 hammers are enough to induce bit flips. So it's more than an order of magnitude reduction, right? And chips on newer DRAM technology nodes can exhibit RowHammer bit flips in more rows and farther away from the victim row. And existing mitigation mechanisms are not effective as future technology nodes. These are the chips that are tested. As you can see, we test in this one DDR3, DDR4, and LPDDR4 chips. LPDDR4, LP stands for low power, and those are the chips that are used on mobile devices mostly. And it shows that all of them are vulnerable pretty much. And yeah, the same observations that I talked about earlier. So here you can see, for example, yeah, just to illustrate. For example, here manufacturer A. When you look at the DDR4 old chips, this is the bit error rate curve for DDR4 old, and this is for DDR4 new. And on the x-axis you have the hammer count, right? So if you look at any hammer count, basically, you can see that more bit flips occur in newer ones, and bit flips occur in smaller hammer counts as well. Okay. And this paper, as the last step, also investigates or analyzes the current, so far all the proposed RowHammer mitigation mechanisms, and shows that if you're using DDR3 old, for example, all these mechanisms are quite good. Okay, let me first introduce the plot. So on the x-axis, we see the RowHammer threshold, or the minimum hammer count to induce bit flip. And it's in the reverse order. So when we go left to right, it actually reduces logarithmically, right? So we are going to future from left to right. And on the y-axis, we see the normalized system performance. 100% means that we do not have any overheads on the system performance. And if you're using old DDR3 chips, you're okay with some mechanisms, right? It's very close to 100% here. And in DDR3 new as well, you're very close. But as you go forward, some mechanisms stop working. For example, this is increasing refresh rate. It doesn't support DDR3 new. And when you look at para, it actually induces quite large performance overheads when you go like really below 100 RowHammer threshold. And the other mechanisms actually do not even scale to that level. So at the time, Twice was the best one at 32K around here. And it has some scaling problems, and it doesn't scale. Basically, you cannot configure for lower thresholds. And the other ones as well were just like some fixed point here. So basically, if you go below this hammer count, which we observed today, these mechanisms induce significantly high performance overheads. So RowHammer is a technology scaling problem, and finding a good solution to RowHammer is difficult. And here is what we saw. Like this is a cartoonish representation of the hammer counts that we observed so far. So in 2014, we were talking about 140 cases in a double-sided attack. And today we talk about 4,800. And if you look at HBM2, it's like 14,000. If you look at DDR4, it's 10,000 activations to induce bit flips. Do you have a question? What about DDR5? So it's hard to put on this plot because Still no FPGA platforms support DDR5 modules that we can, just plug in and test. So we cannot apply the same methodology to DDR5 modules. But on real systems, you can test DDR5 modules. And as I showed earlier in RowHammer paper, they reported some bit Phillips on DDR5 modules as well. Probably the hammer count is a little bit larger in their case because they need to bypass some mitigation mechanisms. Unfortunately, we cannot observe the phenomenon in circuit level for DDR5 yet. Yeah, you can easily port this DRAM bander to DDR5, and you can run the same tests, and it will show you. Okay, I'm not going to go into this. Let's take a break. Can we come back at like, sorry.
Quick question. I mean, the fact that it's quicker with a bit, the more we're progressing with smaller and smaller technology. Is the biggest problem behind it is because we won't be able to notice it as quickly, and the hack will happen quicker? Is that the biggest problem out of it?
Yeah, so it happens really quickly, and you need really like nice detection mechanisms in the hardware. So from software level, it's like really quickly, you cannot observe it even. From hardware, you need to observe it. And it induces high costs in your hardware. So basically, whatever extra you put, you eat up from the chip space, and you could have used that chip space for some other logic as well, right? So we are shooting for like low hardware complexity, and we need higher hardware complexity for accurate detection. That's one problem.
So the faster you do this,
Yeah.
the bigger problem that becomes a hardware issue.
Yeah.
Then it's more expensive.
For the detection side, yes, that's the problem. And for the mitigation side, after you detect, you need to perform some refresh operations to avoid those bit flips, and they take time. So that's also another issue.
Okay, so it's mostly just detection. What the biggest issue is then?
I would say both detection and mitigation. Yeah. I'll talk about some recent update to DDR5 standards that came last year in April. It sort of solves the detection. Basically, it shows that manufacturers are okay with some hardware complexity, but mitigation becomes a problem over there as well. Well, detection is also a problem. Well, yeah, we will talk about all this. Okay. Yeah, let's continue at 5:15 then. Can we test the audio again? Can you hear me now? Can you hear me now? Yes, good. Thank you. Ah, okay. Yes, yes. Now it should be okay. Okay, I guess everyone is back, so let's start. So remember I told you that DRAM manufacturers claim that they fixed the problem. This paper came out in 2020 in IEEE Security and Privacy, right? Do I remember it's correct? Yes. Okay. IEEE Security and Privacy, one of the top venues for security papers, and showed that they are lying. Well, not in those words, but they basically came up with a new access pattern that bypasses the deployed mitigation mechanisms. So this is a poor RowHammer solution that just walks around the mitigation mechanism. So this is the first work to show that TRR protected DRAM chips. TRR stands for target row refresh. This was the naming that industry followed back then, and yeah, they are vulnerable to RowHammer, and mitigations advertised as secure are not secure. And this introduces a new access pattern called many-sided RowHammer attack, and it hammers many rows to bypass TRR mitigations. I will show how. And it also the paper partially reverse engineers the TRR and PTRR mitigation mechanisms. P stands for pseudo, and implemented in DRAM chips and memory controllers. Okay, so it provides an automatic tool that can effectively create many-sided RowHammer attacks for DDR4 and LPDDR4 chips. So here, well, okay, this is the state-of-the-art access pattern that was considered in the past. Let's don't see this part first. And here, the red rows are your aggressor rows. You hammer these two rows, and they together induce disturbance effect on this x-2. And actually, it would be better if I can show it with my pointer. Can you see my pointer there? Probably not. Spotlight. Okay. Oops. Does it work now? Okay, so they hammer x-1 and x-3 to induce bit flips in x-2, and they end up disturbing x-4 and x as well, right? So this is the traditional attack before this paper, and the mitigation mechanisms are designed against this kind of access pattern. So what they do here is that they just go in alternating manner, like this. Blues are victim rows and reds are aggressor rows, and with one row apart, they concurrently hammer 4 rows here, for example, and they call it 4-sided RowHammer attack. And they also change how many rows they hammer together. So on the x-axis, for example, up to 5 rows, they do not observe any bit flips for this one. And then, well, maybe this is a better one. So these are like just the same plots from different modules. On the x-axis, you see like how many aggressor rows that they hammer, and on the y-axis, it's the number of bit flips. So here you see like up to 8-sided access pattern, they do not observe any bit flips. this shows that the deployed mitigation mechanism can detect 8 hot rows and mitigate the bit flips by refreshing their victims. Once you also start hammering the 9th row, then basically the number of counters that they implemented inside the mitigation mechanism becomes insufficient. They cannot track 9 hot rows at the same time. And one of those rows starts inducing bit flips. And you observe bit flips get reduced as you increase the aggressor row count, because as you hammer more rows concurrently, you can put like fewer activations per row because you have a fixed time window to do that. So this is the main idea of this paper. These are the modules that they tested from 3 major manufacturers again. And they also tested some real devices: Google Pixel, Pixel 2, Samsung, Huawei, Sony. These are some mobile phones, if I remember. Yes. And they observe some patterns that reliably induce bit flips in some of them. And they also show that they can mount system-level attacks. They can change page table entries. They can steal RSA keys. They can get pseudo privileges in certain modules among them. And they show that they tested 42 tested DDR4 DRAM modules, and out of them, 13 of them are vulnerable. And out of 13 tested mobile phones, 5 of them are vulnerable. And this is just like this is a, you might find it subjective actually, but there's some supporting evidence as well. This is just scratching the surface. This is some like earlier finding of the deployed TRR mechanisms, and then we also investigated them even more, and I will show that as well. So there are more actually to come. This paper essentially shows that RowHammer is still an open problem, and security by obscurity is likely not a good solution. So I need to open up this a little bit more. When I said the DRAM manufacturers told the media that the DRAM chips are not vulnerable anymore, they actually did not disclose how they solved the issue. They did not explain their mechanisms, and they relied on obscurity. Basically, if you do not know the details of the mechanism, probably you will not be able to induce bit flips. So they relied on this, and it failed. That's what it means here. Security by obscurity is likely not a good solution. So a better solution would be just like putting out the design and then asking all the researchers to attack that design, right? So that they might have even changed the design before deploying it in the real chips. Okay, so JEDEC created a task force, actually. JEDEC is the consortium that defines the DDR standards, and also some like many memory standards, actually. So this is a consortium where there are parties from the memory manufacturers, from the CPU manufacturers, from software companies, and they form a task force together to deal with this RowHammer issues. And they released some updates in 2021. This is about the TRR that is defeated. And in 2024, last year, they needed to release another update to DDR5 DRAM standard. So DDR5, if I remember, first released was in like 2016, 17, something like that. And after some years, they needed to make an update to that just to address the RowHammer issue over there. And I must say that this is not something that frequently happens. JEDEC usually does not change things very easily. And it's really hard to convince them to make any change. But the evidence in the public domain, basically, in these papers, sort of forced them to make these changes. And I will talk about this mechanism a little bit. What they propose essentially is like inside every DRAM row, in a DRAM row, you have 64,000 bits, right? 65,536, like 64K bits. And they say that, okay, next to the 64K bits, let's add like a bunch of other bits as well that keeps the activation count of this row. And whenever we access this row, we open this row, we also update this counter. And then once this counter reaches a threshold, we will update the victim rows next to it. So this is essentially what they propose. And then the problem occurs that, well, I will talk about it when we come to that. Okay. So going back to TRR mechanisms, this is the next paper that we published in Micro 2021. That is a more detailed investigation of these TRR mechanisms. Basically, here we have a methodology that uses data retention failures to understand what's going on inside the DRAM chip. And I'm not going to go into details, but with this methodology, you can observe if a row is being refreshed or not at a particular point using the data retention characteristics of that. And it tells you if the TRR mechanism deployed in the chip refreshed the victim row or not refreshed the victim row. And using this methodology, we tested 45 modules, like 15 from each of 3 manufacturers. And we showed that 99.9% of the rows in the DRAM bank experience at least one RowHammer bit flip if you craft a suitable access pattern after reverse engineering that mechanism. And ECC is ineffective because you can observe up to 7 RowHammer bit flips in a 8-byte data word. This is quite large. So usually the deployed ECC on in the DRAM chips corrects 1 bit in 8-byte data word and detects 2 bits in 8-byte data word. Once you have like 7 RowHammer bit flips, it can lead to like silent data corruption. It can crash your computer. It can create a lot of damage as well. So ECC becomes either ineffective or like you need to really put a very expensive ECC over there. Okay, so I'm not going to go into these details, and let's look at the new RowHammer characteristics. I talked about this paper earlier as well. This is part of my thesis, so I really like it. So in this paper, we look at the sensitivities of RowHammer to temperature. This is, you can consider as access pattern. It's particular aggressor active time and victim DRAM cells physical location. So we tested 272 DRAM chips in this work from 4 major manufacturers. So we covered like up to 98% of the market share, I guess. And we got some takeaways and null observations. So essentially what we show is that a RowHammer bit flip is more likely to occur in a bounded range of temperature if the aggressor row is active for a longer time and in certain physical regions of the DRAM module under attack. And we provide some insights to improve attacks and defenses. So here's an example about bypassing defenses with aggressor row active time. So what we observe is that, so this is on the top is the, sorry, I accidentally click all the time. Okay, so this is the previously known best access pattern. You basically activate row A in this bar and then keep row A active until this point. So this is the minimum time you need to keep a row open once you open it. So there are some timing constraints in the standard. You cannot open close very frequently. So this is basically showing that the previously known best pattern is to activate and pre-charge or open and close rows as frequently as possible. So whenever you satisfy the timing constraint, you send the other command. So instead of doing that, we show that once you open the row, if you keep it on for longer time, you actually exacerbate the read disturbance effect that row creates. And you can, at the end, you can reach to bit flips at significantly smaller hammer counts.
But is the active time something that software can touch, or is that way too deep?
You can do that. Later on in another work, we actually did that. So basically, row buffer locality is something important for performance and energy purposes as well. In a row, you have like 8 kilobytes of data, right? So once you access, you fetch like 64 bytes. And then if you wait a little bit, if you access to another 64 bytes, memory controller starts thinking that, okay, there will be some other parts of this row that will be accessed. So let's keep it on so that whenever a new access comes, we can immediately serve it instead of like closing and opening again. So by exploiting that, so it's a great feature for performance and energy purposes. But by exploiting that, you can keep a row open for some time. Yeah. Yes, very good point. So we first observed this, and then we say that this is something that exacerbates RowHammer. And then we started investigating more, and then understood that it's another disturbance phenomenon called row press. Yeah, this is like a preliminary version of that, basically. Now you see like how it evolved over time, right? This is 2021, and row press is published in 2023. I didn't understand.
You mentioned earlier, like one of the most surface level counters to RowHammer is the count times the row is activated.
Yeah.
And you count it by so many X count pressure.
Yeah.
And then row press would make that defense negligible.
Yeah,
so
because you
was this discovered by scientists, or was this like a new attack that they discovered that they noticed?
No, this is just like our characterization works, right?
So you noticed this while doing research?
Yes, yes.
Oh,
This is yeah.
It wasn't like found by some malicious hacker or whatever, and then
No.
oh no, how do you roll?
I guess it's about the time that a hacker will come up with like, oh, I use row press to do this. Yeah, but yeah, this is like mainly a result of like a lot of research. So the essential thing is like here you can reduce the activation count quite a bit. If you go to row press, you can reduce it down to like 1 activation if you wait for like milliseconds, right? It's not possible, but it's like the extreme case. But you can actually reduce it by like an order of magnitude in realistic cases. And if your deployed mitigation mechanism does not account for this kind of phenomenon, then it's configured for the wrong threshold, basically. So you can bypass it, you can induce bit flips. Okay. Another thing that we found out here is that, let's say this rectangle here, okay, I'll use this. Let's say 100% corresponds to all your DRAM rows. We show that for 10% of the rows, let's say you can induce bit flips at a threshold, let's say HC here, just parameterize it. It's common case across different chips that the remaining 90% of the rows do not experience any bit flips unless you double the hammer count. So it shows that there's a quite significant variation in disturbance vulnerability across different DRAM rows. And you can use this heterogeneity to reduce the overheads of like the hardware complexity of the mechanisms or the performance overheads of the mechanisms and so on. Another thing that we observed is that this is quite curious phenomenon actually. So what we did is we started testing the DRAM chip, and then we repeated tests at different temperatures, and we increased temperature from 50 degrees Celsius to 90 degrees Celsius. And we observed that for many cells, for more than like 98% of the cells, there is a bounded temperature range. So below some lower bound, you do not observe bit flips at the hammer count. And above some other upper bound, you do not observe bit flips again. But in between these two temperature levels, you observe bit flips. So it's really like they're vulnerable at a specific temperature range. And this varies quite a bit across different DRAM cells. So this tells you actually that, you know, it's not really easy to tell if a DRAM cell is vulnerable to RowHammer or not by testing it at a particular temperature. You need to actually test in many different temperature points. For some, let's say you figured out at what temperature point a cell is vulnerable. You can use it in the defense purpose as well. You can use different sets of rows at different temperature levels to reduce your vulnerability, basically. So yeah, I have a full talk about this paper. You can find the link over there. By the way, these slides are on the course web page, so you have all the links. And we have more RowHammer analyses. We sweep voltage. We show that if you reduce the voltage that you use to open the rows, then your voltage swing magnitude is reduced. So as a result, the disturbance effect is also reduced, and it can help you basically mitigating RowHammer. However, it also has some other caveats. As usual, in computer architecture, there is no free lunch. So you sacrifice from row activation latency and data retention time, but there's a nice trade-off point over there as well, if you're curious. We also showed tested HBM2 chips, and we also exploited the spatial variation in different mechanisms as well. But I'm just gonna skip them. Okay, so let's look at new RowHammer attacks and solutions. I talked about half double. So what in this access pattern, what they do is that, let's say, okay, I keep going to there, but I need to show it here. So in classic RowHammer, you have an aggressor row, and you have victims next to that, right? So what this attack exploits really is that the deployed mitigation mechanisms assume a blast radius of 1 row distance, meaning that their basic assumption is that if you hammer this row, this is the row that you affect. And they also do not account for the refreshes that they use for fixing this victim row as an activation. So basically, when you refresh a row, you open the row, wait for some time, and then close the row. It's similar to hammering the row. When you hammer a row, you refresh that row. You induce bit flips in the other rows, right? So what they do is they hammer this aggressor A a lot. It triggers some refresh operations in the immediate next rows here and here. And they also hammer these rows a little bit. And on top of that, these refreshes accumulate. And also this, the activation to this aggressor row A also has some impact in like 2 row distance in some cases. So when you accumulate all these effects together, you can observe bit flips in victim C here. And basically, by doing that, the total activation count that aggressor B receives is below the RowHammer threshold that the mitigation mechanism is configured for. And by doing that, you can actually bypass the mitigation mechanism. So these are all like corner cases that the designer of the mitigation mechanism did not account for. And this is not good for robust designs, right? So you can, you have the full reference here. This is really an interesting paper as well. So this is from Kevin Loughlin and Barış Kaşıkçı and some people, Stefan and Alec from Microsoft and Yatin. What they show here is that, how many people are aware of the word Moesi? Is it familiar? Moesi. Okay, so in multi-core systems, you have your caches, right, for each core. And some of these cores can be used in the same data. So you might end up having different copies of the same data in different caches. Now, if one core updates this, then you need to update propagate that update to other cores as well, so that you do not compromise the correctness of the application, right? So there are some coherence algorithms that are employed in this real chips, and Moesi is one of them. And if I remember, this is based on some Intel chips implementation of Moesi. So these guys basically went to some, if I remember, it was server systems, but it doesn't mention here. So they looked at the memory access patterns of benign applications, a lot of applications. And they figured out that even if there is no attack in your system, you observe some access patterns that are hammering some rows, and then they trace that back, and then find out that kind of sloppy implementation in Moesi protocol actually causes that. You basically like keep trashing cache lines, and then keep accessing to the memory, and then it creates a hammering effect in the memory. So this is really like once while you're implementing that kind of protocol for the cache coherence, it's hard to actually like think about its effects on the memory, like RowHammer as well, right? And it shows that this design slipped out somehow, and it's actually in the wild that, you know, this Moese protocol is causing some hammering effect on some rows, and it can be exploited. But luckily, this paper actually shows some like better design or better implementation of Moese protocol, and it solves the problem already. This is another paper from me. So this is a RowHammer mitigation mechanism that we tackle the scalability and compatibility problems of existing RowHammer mitigation mechanisms. Scalability means scalability with worsening RowHammer, vulnerability with increasing chip density, and compatibility is about the if you can just put that in the memory controller and it works with all the DRAM modules in the field. If you just like build your PC yourself, you know that you get a motherboard, you get a processor. It's just like plug and play, right? You build your computer like a Lego pieces, and then you can just buy a DRAM module and then put it there as well. And once you get sick of your memory because it's slow or because it's low capacity, you can just swap it out. So, but your memory controller actually sits in your processor. So when you change the DRAM module, you do not change the memory controller. And if you deploy some RowHammer mitigation in the memory controller, it's same once your DRAM module has changed. So your mitigation mechanism in the memory controller should be compatible with as many DRAM modules as possible, right? So this tackles that problem. So before this mechanism, basically, there was something that is not accounted for. Okay, I don't have that slide here. I can easily show it here. So let's say a RowHammer attack hammers a row A. Here is row A. And the mitigation mechanisms before block hammer were proposing to refresh row A-1 and A+1 after detecting that row A is being hammered. But there's something tricky in the DRAM chips. You have a hidden address translation inside the DRAM chip. So you provide a logical row address to DRAM chip, but the DRAM chip internally can shuffle the rows, and the logically adjacent rows are not necessarily next to each other in the physical layout. And this information, so this technique is used for like improving yield and improving efficiency in the chip layout, like the place and route stuff. And it's quite important for DRAM manufacturers. It's one of the like added values for them against their competitors. So they actually keep this information proprietary, and you do not obtain that information very easily. So you can refresh A-1, A+1, but they can be some irrelevant rows. And in some other rows, you can still have bit flips. So in such cases, you cannot easily refresh rows, right? So this is what we do. So we detect that there's a RowHammer going on, and we selectively throttle the accesses, particularly to this row address, so that the following accesses will not come frequently enough to hammer that row. And they accumulated, buffered in some buffer, and then they're served together, for example. And as a result, the attacker cannot hammer row A enough number of times to induce bit flips. So it's compatible with commodity DRAM chips in that sense.
The overhead makes it unuseful, but would a solution be to randomize along the layout and then also change this randomization dynamically? Second or something. Goes around, change the attacker can learn.
This is a great direction. You actually explain like a cumulative idea of like several papers that are published in like last 2 years. It's So you can swap rows. Am I okay? You can change the physical row location dynamically. So the overhead is the moving the data, replacing it, right? So data movement is really a hard problem, or like a high overhead thing today, and that's why, like, if you're familiar with processing memory, that's one of the main motivations of processing memory, right? We do not want to spend time and energy to move data around, but there are also some efficient ways of doing that. So are you familiar with row clone? So you can open two rows at the same time in a DRAM bank, and they share their charges in their capacitors, and you can effectively copy one row to another location. So if you have a spare buffer row, for example, you can copy rows back and forth and then change it, for example, right? So there was a, I'm blanking the name of the paper. I forgot. From some Korean researchers, there was a paper doing exactly that. There's another paper that they did follow up. They randomized the row address layout quite a lot. And in a DRAM module, you have multiple. So this is a picture of the DRAM module, right? You have 8 different DRAM chips here. And in some chips, you have extra ECC chips as well in some modules. So that if one of these chips fail, you can correct the bit flips. So they shuffle the rows in a way that the shuffling is not the same in any of those two chips. So every chip has a unique row address layout. And when you do that, as a result of RowHammer attack, your bit flips are accumulated in a single chip. And if you also employ the rank level ECC on top of that, then you can correct the bit flips coming from that chip, and you can mitigate RowHammer quite to some extent, basically. Still not completely solves the problem. There are some corner cases, and you can still like reverse engineer that, craft some access pattern for that, blah blah. But it's a very good direction. There's some good research that's been done. Yeah, if you want to like take a step further on that direction, like I can refer you to the like particular papers in the field in the last 2 years. Any other questions? Okay. So again, main memory needs intelligent controllers for security, safety, reliability, scaling. And there are many different ways, and there are trade-offs. Some industry parties are also publishing papers. SK Hynix published a paper. So this is a very short paper. Actually, you can easily check it. It talks about several different mitigation mechanisms. So it's important that it's from SK Hynix because this is one of the major 3 manufacturers. They talk about per row hammer tracking, multi-step precharge, core bias modulation, like different techniques of mitigating RowHammer. They do not disclose again like which one of that they employed in their systems, but it's a good instance in the literature that talks about some concrete mechanisms. And from this paper, there is actually a chip layout picture that you can see some normal cells here, and you can have a separate row here that contains the counting cells. So you basically put your row activation counters inside the DRAM array. And that's good because DRAM array, so we prefer DRAM as the main memory because of the high density. So when you put your activation counters inside the DRAM array, you have low hardware overhead, and they do that basically. And they also have some probabilistic mechanisms here as well. Okay, so this is the paper from Samsung that I referred to in the beginning of the previous hour, that Google recently published a paper showing that this is not good. Panopticon is a paper from Microsoft, which is a very early version of what is released in the recent DDR5 update today. And this is DDR5 update. And again, they propose putting activation counters inside each row, and it has some effects basically on the DRAM timing constraints, and it changes the interface a little bit. And this was published in April last year, and from April to June we rushed to basically investigate, like really nitpicky, go to that mechanism and find all the caveats, and then we reported them in the DRAM Tech workshop. Now, are we RowHammer free in 2024 and beyond? The easy answer is no, of course. In 2023, we showed RowPress. Some of you are already familiar with that. So the basic question is that what if there's another phenomenon that does not require high row activation count, right? And it's an important question to ask, because if you don't ask this question, you cannot find out these access patterns, right? So in RowPress, I guess there's a good picture here. So this is similar to the access pattern that I explained earlier. When you open a row, instead of closing it as soon as possible, you keep it open for some time, and you have a larger impact on the victim row. And this is called RowPress. RowPress is different than RowHammer because it affects different DRAM cells, and bit flip directionality is also different. So RowHammer and RowPress are really two different DRAM read disturbance phenomena that work together, basically. We tested lots of DRAM chips in this work, and we showed that RowPress significantly amplifies DRAMs vulnerable to read disturbance. And it's a different mechanism. Here you can see that if we keep row open for 36 nanoseconds, this is the distribution of the hammer counts that we get from different rows for RowHammer bit flip. So this is the RowHammer traditional one, right? And once you start applying RowPress, the necessary hammer count to induce bit flip decreases significantly. And you can easily do 7.8 microseconds with today's standards, actually. So you can say that the effective like RowHammer threshold is around like 1000 based on the data on this chip, this paper from 2023. Okay. And we are getting closer to DRAM is doomed. We don't have to rush it. Okay. Well, I will rush it because I think I already explained some of these. So this is how we did RowPress in system level as well. There was a question about this earlier. So in this work, we use the Intel Core i5, and then there's this Samsung module connected to that, and it has a TRR mitigation already implemented inside it. And to make a RowPress attack, basically, so we change the number of cache blocks accessed per aggressor row active time, aggressor row activation. And number of reads is 1 for RowHammer, but we sweep this number of reads parameter so that we access different columns in a row, and then we keep the row open for longer time. And as you can see, like until we access like 16 columns in a row, we do not observe bit flips because the deployed RowHammer mitigation mechanism already fixes the bit flips, refreshes rows accordingly. But once we access like 32 columns, we start seeing bit flips in this particular chip, right? So this means that we reduced the RowHammer threshold quite a bit, not RowHammer threshold at this point, read disturbance threshold, quite a bit by using RowPress. The existing mitigation mechanism does not refresh rows frequently enough, and we bypass it. We also discussed like how we can adapt the existing mitigation mechanisms. Essentially, you can reduce the thresholds, and then you can limit the row open time accordingly, and you have a safe design point basically. And okay, yeah, this is the GitHub link for RowPress. It's artifact evaluated. It's even awarded for the artifact, so you can access to a lot of things over there. So as I said earlier, we have two major directions: understanding bit flips and solving bit flips. And it's not only for DRAM read disturbance, it's for hardware errors in general. And it's not only for DRAM, it's also for flash memories and other technologies. So we have this retrospective paper in 2023 that summarizes everything quite well about RowHammer and RowPress. And we have another paper that's coming. Well, it's not coming up anymore. Okay. It was published last year in DSN Disrupt. This is getting a hybrid access pattern, part of RowHammer, part of RowPress, some RowHammer access pattern, some RowPress access pattern, mixes them together and reduces the time to first bit flip quite a bit. So you can, so we have these two things, and we already showed that using both of them makes things worse, but we didn't reach to the like optimal point, right? So you can try different access patterns and you can make it even better. And we are still working on that. Like we have students working on those. Yeah. So for in the cache, we use SRAM, static random access memory, and it's always powered. So leakage is an issue in terms of the energy consumption over there. But because of leakage, we do not observe like bit flips quite frequently over there. So for the non-volatile memories, some like phase change memory kind of architectures, people expect, people expect for those memory technologies to have some read disturbance effect. And in flash memory, we already have read disturbance effect. It's not exactly the same, but similar. Like once you access some place, a physically closed place shifts their voltage thresholds in flash memory. The access, like how it works is completely different over there. But the phenomenon is quite similar. You read some location and then something changes in a physically nearby location. And in non-volatile technologies, the emerging technologies, they're more worried about the write disturbance, because when you write, you apply a larger current and you create a larger effect over there. So there are not many products out there to test, but there are some simulation-based studies that show that that effect will emerge with the emerging technologies. It's basically like so basically, once you apply like high voltage, low voltage, or high current, low current, you affect the electrons nearby, right? Yeah. So for the current, I believe it should be something like that. For voltage, it's more like you create an electric field, you attract electrons, and then you release those once you go to low voltage, and electrons move back and forth, right? And while doing that, they get trapped in some holes, and once that happens, they create some like weak channels in some leakage paths, so that they exacerbate the leakage that already exists. Yeah. Okay. There are many more works. I'm not going to cover all of those. But yeah, so this is something important, I guess. This is like a positioning paper from Minesh, Safari alumnus. So he revisited the DRAM communication protocols and the isolation of the responsibilities and the knowledge between the processor and the memory, and argued that if we make the DRAM manufacturers more transparent, then there are many things to leverage for our systems. We can reach to more robust systems, higher performance, lower energy consumption. Everything will become much better if we can get more transparency. And this is a similar paper as well. Another paper that I wanted to mention is self-managing DRAM. So here the idea is that so you know the RowHammer story, right? It started in 2012-14, and it reached to 2024 for JEDEC to make a serious update. It took like 10 years, right? And it's quite long. There are many computers and mobile phones manufactured meanwhile, and there are a lot of vulnerable devices out there in the market today. So we do not want this ideally. And this happens because once you need to implement another maintenance mechanism, the adoption of the interface is not happening quite fast. And our key motivation here is that if we move all these maintenance operations inside the DRAM chip, then we do not need to keep updating the interface, and we can let the DRAM manufacturers to update their own maintenance mechanisms and implement the robustness inside the DRAM chip. And for that, self-managing DRAM introduces a simple addition to the existing interface, which is ACT-NAC pin. So what happens is that once memory controller sends an activation command, which opens rows, if DRAM chip wants to perform some maintenance operation, some refresh or some error correcting something over there, then it can send a NAC signal, not acknowledge signal, so that the memory controller knows that DRAM chip is busy and it does not try activating the row again for some time. So this is the addition to the DRAM protocol by this paper, and it allows the DRAM chip to have the necessary time to have to perform all those maintenance operations. So it's already 6 p.m. I will continue a little bit more, but if you need to leave, feel free to leave. If you want to stay, I want to discuss more, of course. Okay, so by leveraging the ability to reject this activation, DRAM chip gains the time to perform those maintenance operations. And by doing that, the paper shows 3 use cases. We can implement DRAM refresh, RowHammer protection, and memory scrubbing completely inside DRAM chip. Memory scrubbing is something that you periodically perform. You basically visit all the locations in your memory, and then you run the ECC on them so that if there's a bit flip already happened, you fix it before they accumulate. So you can also do that inside the memory chip. And there's a full talk about that. And okay, that's all. Should I say anything about here? Okay. So this already shows like that doing so gives us some speed up and it can lower the DRAM energy consumption. This is great, but the main contribution is actually moving the maintenance inside the DRAM chip so that we don't need to keep updating the DRAM interface. Okay, I will skip these papers, but these are also important papers. And I guess these are also in the list of the papers that you can present. So feel free to pick them. These are really great papers. So this is one of my papers. It's really great. I really like it. So I'll just show something in the appendix of this paper here. So we observe in some rows that if you keep hammering the rows, you can actually observe that the RowHammer threshold goes lower a little bit in some of the rows. So this is some motivational data at best for like proper agent studies. And as I said earlier, like for understanding RowHammer part, we do not still have a good understanding of how DRAM ages. So this is a motivational data for that. Okay. So we have some other papers that are recently published. RowHammer identifies that the existing RowHammer mitigation mechanisms can be exploited to mount denial of service attacks, and it protects them by using some throttling mechanism over there. So this is DRAM-Sec paper that I mentioned earlier, and Kronos is the extended version of that paper that is published this week. Actually, it was presented yesterday in Las Vegas. So in this paper, we identify the shortcomings of the industry's best solution, which is like which came with the last year's update. And we pinpoint like where it sucks, basically. And then we propose an alternative design for the same substrate so that we can get rid of those overheads. And what we do is we basically, well, I need to get into a lot of details to explain it. So I really encourage you to look at that. Probably soon you will have a YouTube video as well from the presentation of that. So in 2024, we had like RowHammer sessions in multiple conferences. So RowHammer is still relevant. This DRAM Sec workshop, it's focused on DRAM security. But if you look at the titles, it's purely about RowHammer in the last year's version. This year we are organizing it. So let's see what we will have. We had another session in micro earlier this year. And this week, the HPC conference is happening, International Symposium on High Performance Computer Architecture. This is one of the like 4 major conferences in computer architecture. And we have 2 sessions dedicated to RowHammer. And both of them were yesterday. So we're having like 6 new papers in the literature as of this week. Not all of them are from us. These are not from us. These 3 are from us. Okay. I'm not going to go into these. And then I'll say that, okay. Okay, I'll get to the key takeaway: intelligent memory controllers enhance robustness and enable better scaling. So we need to have better controllers. We need to understand the problem better. We need to come up with better architectures, and we need to design and test properly and rigorously. And we need infrastructures for those. We have the infrastructures, and we keep building new infrastructures so that we do not have this kind of broken bridges. And with intelligent memory controllers, we can avoid such issues, not broken bridges, but broken computers. And main memory needs intelligent compute. Okay. So we want fundamentally robust computing architectures. And what we see in RowHammer-like things, this is final few slides. What we see in RowHammer domain is that it can be classified as like sort of Byzantine failures. And it's because we can characterize these undetected erroneous computation, but it is opposite of fail fast. So it's not very easy to identify when it fails. And you need to do rigorous testing for that. And it's very difficult to detect. And you must do all you can do to avoid them, basically. Because as like honest researchers, if you do not do like rigorous testing, and if you do not build the literature enough to understand this well, there are always like smart hackers out there to exploit these. Okay, this is the paper that's proposed, defines Byzantine generals problem. Okay, so before RowHammer, there were some memory-based attacks. So here they put a heater or ultraviolet stuff here that emitted some light beams to the memory to induce bit flips. And by doing that, they attack some virtual machines. And today, you can do that via software, without that kind of hardware, by using RowHammer. So it changed the perspective quite a bit. So many RowHammer and bit flip attacks are coming up every year. And we have many new solutions in the industry that start with Apple security release and Memtest 86 update. And we also have the update to the JEDEC standards today. So this is a shift of mindset. And it's a general purpose hardware. It shows that general purpose hardware is fallible and it's exploitable. And it's not a coincidence that 2 of the groups that discovered Meltdown and Spectre heavily worked on RowHammer attacks. So these are all relevant. These are like hardware vulnerabilities that are exploited from software. In conclusion, memory reliability is reducing. RowHammer is a prime example. Bad news is that it's getting worse. But good news is that we have a lot more to do. And next, I guess we need to look at silent data corruptions a little bit more, because these intermittent effects can cause silent data corruption, and it might be really hard to detect in the wild, and they might be exploitable. And there are some references here for some silent data corruption papers that you can take a look. And okay, so the takeaways are both memory and logic errors will become worse with technology scaling. Hardware errors will create worse robustness problems, and we cannot afford ignoring data corruption. It's really important. So this is the Safari group. I'm not sure why we have all these slides here, but it's like basically appreciating everyone. This is our GitHub repo. Like, we have a repo for pretty much all the papers that I showed today, and you can look at the raw data, look at the simulation infrastructure, you look at the experimental infrastructure, and you can also get hands-on if you collaborate with us. Come to our lab and start running some experiments on our infrastructure. You can basically test real DRAM chips. And we have a simulation infrastructure, Emulator 2.0. Jikun over there put quite a bit of effort recently to Emulator 2.0. DRAM Bender is the DRAM testing infrastructure. And we don't only have the infrastructure, we also have like full-fledged lectures for PNS courses that explain how you can use this infrastructure. Okay, this is all. I'm done with 10 extra minutes. Sorry for the delay. Are there any burning questions?
Earlier we discussed the randomly moving whole rows around, right?
Yes.
Would it be viable to use the counters to either decide which rows to completely move, or just to decide which rows to prioritize to move? Reduce how much data just flows?
Yeah, exactly. So now you're like, instead of blindly and randomly moving data, you just do it in a more educated way. You track the activation counts, and then whenever a row is hot, you move it, I guess, right?
Yeah.
Yeah, so it's a good idea. I guess the papers that I mentioned already do it as well. I guess the first paper that mentions it is Crow from Hasan Hassan. It's the bird crow. You can search for it, and there's also a reference in the. But if you shoot me an email, I can also send it related papers.
Okay.
Yeah.
So
It's good direction. Yeah. What?
Crow like the animal.
Yeah, the bird,
Oh,
the animal
yeah.
crow. Yeah, that's the paper's name. One version is copy row. Other thoughts? Okay. I guess we can finish it here then. Thank you very much for staying.